Yeah, we'll start in a sec. There is a human in the loop. If you have any questions about BioniChaos.com, go for it. Chaos.com. Again, there is a human in the loop. If you have any questions about any of the content on BioniChaos.com, do let me know. I'll try and answer your questions or comments. Oops, I forgot to go live on LinkedIn. So we are streaming on YouTube and LinkedIn. Your questions. Yeah, there is a human in the loop. If you have any questions about BioniChaos.com content, pop it in the chat and I'll try answering that. Yeah, I'll be doing this interactive brain EEG simulation. It's focusing on principal component analysis and independent component analysis. Hopefully you find it interesting. We'll get the robot to do a quick overview first.
Have you ever paused to consider what your brain actually sounds like?
Hmm.
Or, how scientists manage to peek into that incredible electrical symphony that's constantly playing out inside your head? It's a pretty wild thought, right?
It absolutely is. Our brains are these complex, incredibly busy places,
Mhm.
and trying to figure out what's going on from the outside.
Well, sometimes it feels like trying to understand an entire city's conversations just by listening from space.
Right. Exactly. And today we're taking a deep dive into something really fascinating, an interactive brain EEG simulation.
Ah, EEG.
Yeah, electroencephalography. It's this remarkable tool that doesn't just let you visualize these electrical signals, but actually hear them.
Which is pretty cool.
Totally. So our mission for this deep dive is to unpack this captivating world of brainwaves, get a handle on the clever techniques used to make sense of these really complex signals,
Mhm.
and show you why this interactive approach is, frankly, a game changer for learning about neuroscience.
Mhm.
We're going to explore how that veritable cocktail party inside your head can actually be understood,
Yeah.
and how we can effectively listen in.
And what's fascinating here is that we're talking about a technology, EEG, that offers this dynamic, real-time window into the very mechanics of consciousness. It's not just, static data points.
It's alive.
It's a living, breathing electrical landscape.
So, okay, let's start our journey into this electrical symphony.
Mm.
What is EEG, really?
hmm
At its most basic level, how does it pick up what's happening inside our skulls?
Well, at its core, EEG records the electrical activity of the brain You do that by placing electrodes on the scalp.
Okay.
Now, it's really crucial to understand what it's not picking up. These aren't the direct electrical zaps of individual neurons firing one by one.
Ah, right. Too small.
Far too tiny and too fast. Instead, what EEG captures is the collective electrical field. It's generated by millions, literally millions, of neurons firing together synchronously.
Like a crowd cheering all at once.
Exactly. And that collected activity then ripples and spreads through the brain tissues, through the skull, right up to the surface of the scalp.
And this phenomenon, it's called volume conduction. And that's precisely why we get such a complex, sort of averaged mixture of signals at each electrode we place.
That makes perfect sense. It's not one voice, it's the whole choir blended together.
Precisely.
And speaking of complex mixtures, this brings us to what researchers playfully call the cocktail party problem. It's a fantastic analogy, but tell us more. How does it apply here?
Absolutely. Okay, imagine you're at a really crowded party, a very crowded party.
Okay, I'm there.
There are dozens of conversations happening all at once, right? Everything's blending together into this cacophony.
Yeah, hard to focus.
Exactly. Trying to isolate and understand just one conversation is incredibly difficult because all the sounds are mixing. And that's precisely the challenge with raw EEG recordings.
Ah.
Every single electrode on your scalp is picking up this jumble of electrical signals from various brain regions, all mixed up together, just like those voices at the party. And the interactive simulation we're digging into today, it actually models this exact real-world challenge. It lets you see how those different brainwave patterns, starting from various sources, combine at the scalp electrodes.
So you can see the jumble happening. But it's not just a mess of noise, though, is it? Our brains produce distinct types of conversations, these brainwaves.
Right.
Delta, theta, alpha, beta, gamma, we've all heard the names. But what's really remarkable is how distinctly these different rhythms show up in that electrical symphony.
Indeed. And these aren't just arbitrary frequencies. They actually correspond to different states of consciousness, different cognitive processes. It's quite meaningful.
So let's break them down.
Okay. First, we have delta waves. These are the slowest, typically ranging from about 0.5 to 4 hertz, so really slow.
Like a deep bass note.
Exactly. These dominate when you're in deep, dreamless sleep. They're like the brain's deepest, most fundamental hum. Really important for restorative processes.
Okay, delta for deep sleep. What's next?
Then there are theta waves, a bit faster, say 4 to 8 hertz. You'll often see these during drowsiness, maybe light sleep, or even deep meditation.
That kind of floaty feeling.
Yeah, associated with creativity, that sort of hazy, introspective state right before you drift off or when you're deeply relaxed.
Makes sense. And alpha. I hear about alpha a lot.
Right, alpha waves are very well known. They're between 8 and 13 hertz. These become prominent when you're awake but relaxed, maybe daydreaming, meditating, or just resting quietly with your eyes closed.
So calm but awake.
Exactly. It's that calm, clear-headed state where your brain is kind of idling, ready to engage, but not actively processing a heavy load.
And when you are processing that heavy load, like concentrating.
Right. When you're really getting things done, actively thinking, concentrating, solving problems, your brain shifts into beta waves. These are faster, ranging from about 13 to 30 hertz.
That's the on switch.
Pretty much. This is your brain in go mode, focused and engaged, processing what's coming in from the outside world.
And the last one, gamma.
And finally, the fastest, and you could argue the most enigmatic, are gamma waves. Typically from 30 hertz up to maybe 100 hertz, sometimes even higher.
Wow, fast.
Very fast. These are associated with higher level cognitive functions, intense focus, perception, even consciousness itself. They're thought to help bind together different brain regions to create a unified experience.
It's like putting puzzle pieces together.
Sort of, yeah. Like when you integrate all aspects of seeing an object, its color, its shape, its movement into one single perception, gamma might be involved in that binding.
It's truly incredible to think that all these different rhythms are playing out in your head constantly, weaving together to create, well, you.
Absolutely.
And that's where this interactive simulation really shines, isn't it? You don't just read about it. You can actually play with it, get your hands dirty, so to speak.
Exactly. This simulation provides a really hands-on way to explore these complex dynamics. It models how those different brainwave patterns, starting from different brain locations, combine at the scalp electrodes. It lets you visually and audibly understand that cocktail party unfolding.
So how does it work? What can you actually do in the simulation?
Well, you can start by playing with the presets. They call it preset power, which is kind of fun.
Okay.
They're fantastic for getting an instant feel for different brain states. For example, there's a relaxed preset. Click it, and boom, you see prominent alpha waves, maybe some theta activity, just like when you're meditating or chilling out.
Instantly visualizing calm. Cool.
Yeah. And for a sharp contrast, you click the active task scenario. That simulates focused cognitive work, and you'll see those dominant beta and gamma frequencies light right up.
So you see the brain getting busy.
Exactly. There's also a noisy data preset, which is really useful. It vividly demonstrates those real-world challenges, showing high levels of artifacts that can really obscure the actual brain signals.
Shows you what scientists are up against.
Right. And if you just want to see everything happening at once, the complex mix shows a rich combination of all the frequency bands simultaneously. So these presets are great for quick, targeted exploration.
But here's where it gets really interesting and fun, right? The manual mode.
Ah, yes, manual mode. This is where you become the conductor of the brain symphony, in a way.
How so?
You can literally click on the brain diagram in this simulation to place your own signal sources, up to 5 different ones.
So I decide where the brain activity is coming from.
Precisely. And you watch in real time how the electrode readings change as you add these sources in different locations. You'll instantly see that sources closer to an electrode have a much stronger influence,
Makes sense.
while sources further away contribute more weakly. This brilliantly lets you directly see one of EEG's core characteristics, its spatial resolution, or sometimes its limitations.
What do you mean?
Well, signals generated closer to the scalp, or from large groups of neurons firing together, they show up much more clearly at nearby electrodes. But activity deep within the brain, or from smaller, scattered groups of neurons, much harder to pinpoint accurately from the scalp.
Ah, okay. So it's great at when something happens,
Excellent temporal resolution. Millisecond precision.
but maybe less precise on the where.
Exactly. Especially for deep sources. This simulation lets you see that trade-off interactively.
That's super insightful. And you mentioned hearing it.
Yes. And this is, for many people, the coolest part. There's an optional audio feature. This converts the EEG signals directly into sound. Yeah. It gives you this intuitive, almost visceral way to hear the different frequency characteristics of each brainwave type. Delta sounds like a slow thrum, gamma, like a high-pitched buzz.
You can literally listen to the brain's rhythm change.
You can. And this sonification technique, it's not just a gimmick, it's actually used in real-world neurofeedback applications.
Neurofeedback.
Yeah, where individuals learn to modulate their own brain activity by listening to or watching real-time representations of their neural signals. Imagine hearing your own brain calm down, hearing the alpha waves get stronger as you relax.
Wow. That idea of hearing your brain's rhythm, that's fascinating. What practical things could you do with that sonification beyond just visualization? Can you really learn to control your brain activity?
Well, that's the goal of neurofeedback. Precisely. It provides this immediate, intuitive feedback loop. The brain is surprisingly good at learning from these kinds of cues.
So it's like training your brain using sound.
In essence, yes. Beyond neurofeedback, it's also being explored in areas like, say, sleep research. Distinct sound patterns could indicate transitions between sleep stages. Or even in gaming, imagine your brain state influencing the game's atmosphere or difficulty.
Okay, my mind is slightly blown.
It's a very direct way to interact with your own neural landscape. And to fine-tune your view in the simulation, there are other controls too. There's a noise slider.
Ah, back to the real-world problems.
Exactly. It lets you see how signal quality affects the analysis. You can crank up the noise to simulate really challenging recording conditions, maybe like trying to get a clear EEG on a toddler who just won't sit still.
Laughs. I can definitely picture that.
And then there's a timescale control. This adjusts the temporal resolution of the display. You can zoom in to see really rapid oscillations or zoom out to see longer-term patterns unfolding over seconds.
Seeing the forest and the trees.
Exactly. It's about choosing the right perspective for what you want to see.
So these controls let you adjust the view, but they also kind of highlight the challenge, right? No matter how you display it, you're still dealing with that jumble of signals at the scalp.
That's right. Which brings us right back to that cocktail party problem. How do you pick out the individual conversations from this complex mix? How do you unmix the signals?
That's the million-dollar question, isn't it? Seeing the overall activity is one thing, but how do scientists pull out the useful, independent bits from all that noise?
This is where some powerful signal analysis techniques come into play.
Hmm.
And the simulation actually lets you apply 2 fundamental ones.
Okay, let's hear it.
The first is principal component analysis, or PCA.
PCA, heard of it, but what does it actually do with brainwaves?
What PCA does is it reorganizes the mixed signals based on their statistical variance. Essentially, it looks at all the electrode data and finds the directions or patterns in which the data varies the most.
So it finds the dominant trends.
Exactly. When you click Apply PCA in the simulation, the channels get reordered. The components, the patterns, with the highest variance, they get shown first.
So it's like finding the loudest voices in the room, maybe, even if you can't tell exactly who's speaking or what they're saying.
That's a pretty good analogy. It helps reduce the complexity of the data and shows you the strongest signals, the biggest patterns.
But maybe not necessarily linked to one specific spot in the brain?
Right. It's more about data compression and highlighting the strongest statistical trends. The resulting components might be mixtures themselves, and they might not correspond directly to physiologically meaningful sources in the brain.
Okay, useful, but limited for finding the real sources.
It often is, yes. For that, we typically turn to a more sophisticated technique, independent component analysis, or ICA.
Ah, okay, so ICA is designed to actually isolate those individual voices in the brain's cocktail party, not just the loudest combined sounds.
Precisely. ICA is what we call a blind source separation technique, while PCA looks for variance, for patterns that often occur together. ICA looks for signals that are statistically independent from each other.
Independent. What does that mean in this context?
Think of it as assuming that each distinct brain process, like a specific thought pattern or a motor command to move your hand, or even an artifact like an eye blink, generates its own unique, separable voice in that crowd.
Okay.
ICA's algorithm tries to mathematically untangle these signals based on the assumption that these underlying sources don't predictably change together. They're independent.
So it's trying to reverse the mixing process.
Exactly. And the real breakthrough with techniques like ICA isn't just about cleaning up messy data. It's revealing that beneath the apparent chaos of millions of neurons firing, there seem to be these remarkably distinct, independent voices.
Meaning our thoughts or perceptions.
Or even just you blinking your eyes.
They have their own unique, separable neural signatures.
That's the idea ICA works on. And it's critical for truly understanding how the brain might be organized, how different functions might operate somewhat independently.
And how does the simulation show this?
This is where it gets really interactive and, again, kind of fun. When you activate ICA mode in the simulation, it shows you these estimated source signals that is calculated.
Okay.
And then this is the cool part. You can hover your mouse over each waveform, each estimated source.
Yeah.
And the simulation will actually highlight which brain location that signal most likely corresponds to. The relevant source area will glow on the brain diagram.
Whoa. So you see the signal and where the simulation thinks it came from.
Exactly. It vividly illustrates that spatial-temporal relationship, the link between the signal over time and its estimated place in the brain.
That's incredibly powerful to see the source light up as you analyze its signal. But if ICA is so good at isolating these independent sources, what are its biggest limitations in, the real world? Is there ever a conversation? It just can't disentangle.
That's an excellent question. While ICA is incredibly effective, powerful stuff, its main limitation is that core assumption. It assumes the sources are statistically independent.
And sometimes they aren't.
Well, neural processes can be highly interconnected, so that assumption isn't always perfectly true for every single thing happening in the brain. Also, it's a computational process. If the data is very noisy, or if you don't have enough electrodes,
Right?
it can still be challenging to perfectly separate every single component. Sometimes signals remain mixed, or a component might represent a mix of things. But despite that, its utility is absolutely immense.
So, okay, stepping back from the simulation, what does all this mean for the real world? How are PCA and ICA actually used outside of this, fun learning tool?
Oh, massively. Understanding these techniques is absolutely crucial for interpreting real EEG data in both clinical work and research.
Like what? Give us some examples.
Okay, a big one is epilepsy monitoring. ICA is invaluable there.
Yeah, so.
It helps doctors separate out the actual seizure-related brain activity, the stuff they really need to see, from common artifacts like muscle tension from jaw clenching or eye blinks or electrical noise.
Things that could otherwise hide or mimic seizure activity.
Exactly. These artifacts can totally obscure the true neural signals and make diagnosis incredibly difficult. ICA helps clean that up significantly.
Yeah, it makes perfect sense. Critical for diagnosis. What about brain-computer interfaces? That always sounds like straight out of sci-fi.
It does, doesn't it?
Yeah.
But they're very real, and these kinds of techniques are right at their core.
Really?
Yes. In brain-computer interfaces, or BCIs, techniques like ICA enable the extraction of specific neural signals, like the intention to move left or right, which can then be translated into commands to control external devices.
Like moving a cursor on a screen with your thoughts.
Or controlling a prosthetic limb, yeah. Imagine thinking a command, and your specific brainwave pattern is precisely isolated and translated into action.
That's incredible potential. What's the biggest hurdle stopping that from being, like, everywhere?
Oh, there are many. Reliability, speed, training time, making the systems robust outside the lab. Yeah. It's complex. But the core signal processing relies heavily on isolating those command signals from the background brain activity.
Astounding. And I bet sleep research uses this heavily, too.
Absolutely. Sleep researchers use similar methods all the time to identify the different sleep stages.
Because each stage has its own brainwave signature.
Exactly. Each stage, light sleep, deep sleep, REM sleep, has its own unique mix of delta, theta, alpha, beta activity. These techniques help researchers accurately distinguish them, which is critical for studying sleep disorders or just understanding sleep's role in memory and cognition.
So, okay. This simulation is clearly fantastic for learning, for demonstrating these complex ideas in a really fun, accessible way. But I'm guessing real-world EEG analysis has, well, a few more hurdles than what we see in this nice, clean, digital environment.
It definitely does. This simplified simulation gives you a really strong foundation, a great intuition, but actual recordings contend with a lot more complexity.
Like what?
Well, you're dealing with all sorts of real-world artifacts. We mentioned eye blanks, muscle tension, electrical interference from lights or computers, even tiny head movements. All of that can contaminate the signal you care about.
More noise in the cocktail party.
Much more noise. Plus, the brain's own physical structure, the skull, the tissues, creates complex conductivity patterns. These affect how signals actually propagate to the scalp. Figuring out where a signal originated inside the brain based only on scalp recordings. That's called the inverse problem.
And it's hard.
It's notoriously difficult, very complex mathematically. And of course, modern EEG systems often use way more electrodes than the simulation shows. Often 32, 64, even 128 or 256 electrodes.
To get better spatial detail.
Exactly. To improve that spatial resolution and get a more detailed picture of where things are happening.
And, you know, it's a testament to the complexity that even building this kind of sophisticated interactive tool must have its own challenges behind the scenes.
Oh, absolutely.
Thinking about making sure the visuals work on different screens or managing all that signal data streaming in real time so it doesn't crash.
Right, or preventing subtle audio glitches or memory issues when you're converting electrical signals to sound constantly.
It's a massive software engineering challenge to make something so complex feel so seamless and intuitive, so fun for the user.
Indeed. It really highlights the intricate engineering that goes into making these powerful neuroscience tools accessible. And it also underscores why these signal processing techniques like PCA and ICA are just so vital. They're the bridge between that messy, noisy raw data and actual meaningful scientific insight.
So, wow, we've taken quite a journey.
Yeah.
From understanding the electrical symphony of the brain and that tricky cocktail party problem to exploring it interactively with these cool presets and even manual controls in the simulation, you've shown us how powerful techniques like PCA and ICA help us try to unmix these signals and how crucial these concepts are in the real world. Epilepsy, BCIs, sleep. It really makes you think about the incredible complexity buzzing away in there. Even with all these advanced tools, we're still just scratching the surface, aren't we?
We really are. And if we connect this to the bigger picture, the field of EEG is evolving incredibly rapidly. It's not standing still.
What's coming next?
Well, we're seeing really exciting advancements. Things like machine learning being used for automatic artifact removal algorithms that learn to spot and remove noise even better than traditional methods.
Making the data cleaner faster.
Exactly. There's also progress in real-time source localization, using individual brain anatomy, maybe from an MRI scan, to pinpoint where signals are originating with much better precision, practically as they happen.
Combining the when of EEG with better where.
Right. And integrating EEG with other neuroimaging tools like fMRI, which is great for spatial detail, or MEG, another technique measuring magnetic fields. Combining these gives researchers a much more comprehensive view of brain activity.
Getting the best of all worlds.
Trying to, yeah.
And here's where it gets really interesting for the future, I think. You hear about deep learning models.
Yes. They're now being developed to try and decode complex cognitive states, maybe even intentions, directly from EEG signals.
Seriously, like reading thoughts?
Well, reading thoughts is a strong term, but maybe identifying patterns associated with specific mental states, emotional states, or even decisions with increasing accuracy. Imagine gaining deeper insights into how we think, feel, or choose just by analyzing these brainwave patterns in new ways.
The possibilities seem huge.
They are. And beyond the lab, think about the development of portable wearable EEG systems.
Right, like headsets you can wear anywhere.
Exactly. This is enabling brain monitoring outside traditional restrictive laboratory settings. It's opening up entirely new possibilities for understanding how our brains work in natural environments during everyday life.
That's a game changer.
It really could be. So yeah, EEG remains this remarkably valuable window into the electrical symphony of neural activity that underlies, well, everything: human consciousness, behavior.
Right.
It's a symphony we're still learning to fully compose and comprehend.
It truly is a symphony that never stops playing, and one we're continuously finding new ways to listen to, analyze, and understand. So what stands out to you from this deep dive? We really encourage you to continue your own exploration into the fascinating, complex, and, as we've seen today, incredibly fun world of neuroscience.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
You know that feeling, right? You're staring at your screen, maybe trying to wrestle with a tough report or really dive deep into studying. And then, almost without thinking, you reach for your headphones, hovering over your music playlist. Does it actually help you focus? Or is it just like another layer of distraction? What's really going on inside your brain when the music starts? Today, we're doing a deep dive into exactly that. There's this fascinating new study that used, well, a whole suite of advanced sensors to look at working memory, not just with music playing, but with music as an active component. We're not just talking background noise here. It's about exploring music as a potential tool, a non-invasive one, to actually regulate our cognitive states. So our mission today is to unpack how researchers are using this really cutting-edge tech to understand that brain-music dance, why it matters for things like, focus and performance, and what surprising insights this kind of multimodal data can offer you. It's a really cool look at how something so common could be key to unlocking our cognitive potential. Okay, let's get into it.
It really is an exciting area. I mean, for ages, music's been seen mostly as, well, aesthetic, right? Something for enjoyment, setting a mood. But the study really highlights how we're moving into an era where we can measure its actual physiological and cognitive effects, measurable ones. It sort of shifts our whole perspective from music as just passive enjoyment to potentially an active intervention.
Active intervention. I like that phrase. Makes you think differently about your go-to playlist, doesn't it?
Yeah.
The idea that music isn't just for fun, but could literally actively change our brain state. That's pretty wild. Not just mood, but like a brain tool.
It is wild, but there's a solid foundation for it. The theoretical underpinning, it goes back to a really fundamental concept in psychology, the Yerkes-Dodson law. This law basically suggests there's a kind of sweet spot for cognitive arousal, an optimal level where your performance peaks. Think about it. If you're too chilled out, maybe Under-aroused, your mind wanders, performance dips. But if you're too stressed, over-aroused, you get overwhelmed, make mistakes, your output drops.
Right. So it's not about being hyper alert or totally zoned out, but hitting that perfect Goldilocks zone, that middle ground. So this study was asking, could music be the thing that helps us find that zone, kind of nudging us towards peak performance?
Precisely. They're looking at whether music can non-invasively help regulate our arousal and performance to get us into that sweet spot. What's really interesting is how they're thinking about using this. It's not just confirming a feeling we have. They're measuring it, quantifying it.
Okay, that immediately makes me think, what does this mean for, just everyday folks trying to focus, or maybe someone dealing with concentration issues, or even like someone recovering from a brain injury? This sounds like it goes way beyond just a productivity tip.
Oh, absolutely. If you look at the bigger picture, this kind of research is really foundational for developing highly personalized ways to regulate brain states without drugs or invasive procedures. Imagine, maybe in the future, a specific music prescription could help a student stay focused during a really complex task, or maybe assist someone in neural rehab after a stroke to boost memory. It has huge implications for cognitive impairments and even for designing next-gen brain-machine interfaces that work with our brain's natural rhythms. This isn't just abstract theory. It's got really tangible, exciting applications.
That's genuinely incredible. So to understand how they even started looking into this huge idea, we probably need to get into the details of the experiment itself. They use something called the NBAC task. I know that's a classic in cognitive science. Can you break that down for us?
Yeah, the NBAC task is, well, it's a standard for a reason. It's a very effective way to measure working memory and cognitive load. So here's how it works. Participants see a stream of stimuli, one after another. In this study, it was single letters. Their task is to decide if the letter they're currently seeing matches the one that appeared and positions before it in the sequence. So for one back, you're just checking against the immediately previous letter. Pretty straightforward. But for three back, you have to remember the letter from 3 steps ago.
Wow, yeah, that sounds mentally taxing. I can feel my brain churning just thinking about 3 back. So increasing the N really cranks up the difficulty then.
Exactly. That's the point. The researchers here focus mainly on 2 levels. 1 back, which is relatively easy. You just hold one item in mind. And then the 3 back, which significantly ramps up the cognitive workload. You're constantly updating what's in your memory, ditching old letters, grabbing relevant ones, all under time pressure. It's designed to push your working memory.
Okay, and this is where the music comes in, right? Participants didn't just listen to random background music. They actually brought their own calming and exciting tracks. That's where it gets really interesting. How did they weave the music into these demanding tasks?
Yes, that personal music choice was really key. The idea was to get genuine emotional and physiological reactions. So the experiment had 2 main sessions. In one session, people did the NBAC tasks while their chosen calming music played. In the other session, same tasks, but with their exciting music. Each session was about 16 minutes long, and it was broken down into several task blocks.
And within those 16 minutes were the easy 1 back and hard 3 back tasks all mixed up.
Yep, perfectly mixed and randomized. That avoids any bias from doing all the easy ones first, for example. Each 16-minute session had an equal number of 1 back and 3 back blocks, actually 8 blocks of each, so 16 blocks total per session. And inside each block, there were 22 trials, so 22 letters to respond to. They managed the timing really carefully, too. Short 10-second breaks between blocks, a slightly longer 20-second break halfway through the 16 minutes, and then a proper 2-minute rest after each full session. It was very controlled.
And who are the people involved in this pilot study? I know these deep brain studies often start with a smaller group to collect really dense data.
That's right. They initially recruited 11 participants. But the really comprehensive multimodal data, meaning, where all the different sensors worked perfectly, it gave usable data that came from 5 individuals, subs 3, 4, 6, 8, and 11. It just underscores how complex this kind of research is. You need every single technological piece working just right to get that full picture.
Right, and this is where the tech side just gets amazing. They weren't just measuring 1 or 2 things, you said a whole suite of sensors. What exactly were they measuring to get inside that mind-music link?
It really was a symphony of sensors, as you put it earlier, each one playing a crucial part. So first, they gathered a whole array of physiological signals, things like skin conductance, you might know it as EA, electrodermal activity, that's a great indicator of your autonomic arousal, basically how activated or stressed your body is unconsciously. They also had ECG for heart activity, skin surface temperature, respiration rate, PPG photoplethysmography, which tracks subtle blood volume changes linked to heart rate variability, and EMG, electromyogram, measuring muscle tension. So these give you a window into the body's automatic responses.
Okay, so that's the body's sort of background reaction, but they also look directly at the brain, right?
Exactly, that's crucial. For direct brain activity, they used FNIRS, functional near-infrared spectroscopy. This is a really neat piece of tech because it non-invasively measures changes in blood oxygenation in the brain. Essentially, it shows where the brain is working hardest. And FNIRS has some real strengths. It gives better spatial resolution than EEG, so you can pinpoint activity more precisely. Plus, it's portable, which is great for studies like this. It's especially good for looking at the prefrontal cortex, which is super involved in memory tasks like NBAC.
And then, obviously, besides all the body and brain signals, you need the bottom line. How did people actually do on the tasks?
Absolutely. That's the behavioral data. It's essential for understanding performance. They tracked every single response, correct, incorrect, and how fast people responded, the reaction time for each letter. And one more thing, they also captured de-identified facial expression scores. So another layer of observable response potentially indicating emotional state.
Okay, wow, that is a lot of data streams. So why? Why go to all that effort? Why strap on so many sensors? Isn't like one signal enough to tell you if someone's stressed or focused?
That's a really good question, and it hits the nail on the head about why this multimodal approach is so powerful. While, yeah, a single signal like skin conductance can tell you something useful, collecting all these diverse signals lets researchers capture complementary aspects of what's happening. It's like each sensor tells a slightly different part of the story. Skin conductance tells you about arousal, FNRS about brain workload in specific areas, reaction time about performance efficiency. Put them all together, and you get a much richer, more complete picture of the brain's overall response to both the cognitive challenge and the music.
Ah, I see. It's like assembling a puzzle, right? Each sensor gives you a different necessary piece to see the whole image.
That's a perfect way to put it. This holistic view can lead to much more robust biomarkers of cognitive states, like stress or focus. You're not just relying on one data point. You're seeing a pattern across multiple systems: physiological, neurological, behavioral. Imagine, like, you see not just a dip in FNIRS activity suggesting overload, but at the same time a spike in skin conductance and maybe a subtle shift in facial expression towards frustration. That combined signature is a far more reliable indicator of cognitive overload than any single measure could be on its own. It could lead to a sort of stress fingerprint. It helps us build a really deep understanding of the mechanisms at play. Now, it's really important to remember, this was a pilot study, a foundational piece of work, so the sample size was small. But what they successfully showed was the feasibility of using music this way as a safe, non-invasive method to potentially regulate cognitive states. Specifically, they were able to decode arousal levels pretty well from the skin conductance data and performance levels from the behavioral data, which suggests this whole multimodal approach really does hold promise.
Okay, that's still a huge step, showing it's even possible. So, building on that success, what are the really exciting potential applications down the road if we can refine this stress fingerprint idea you mentioned?
Oh, the potential is really quite something. This research genuinely opens the door for highly personalized, non-invasive ways to manage our cognitive states. Think about music tailored specifically to an individual's unique brain responses. Not just calming music in general, but your specific calming music profile. Maybe a personalized audio stream helps a surgeon maintain intense focus during a long operation, or helps a student power through difficult problem solving without hitting cognitive burnout by actively managing their arousal level. And the implications for neural rehabilitation are massive, helping people regain cognitive function after injury, plus developing new non-drug treatments for cognitive impairments. It really shifts music from just background sound to potentially a precision therapeutic tool.
A truly personalized brain tuner.
Yeah.
Amazing. But like all pioneering research, especially pilot studies, there are always limitations, right? Things that point the way for future studies. What did the researchers themselves flag as the next steps?
Yeah, and they were very clear about the limitations, which is exactly what you want for good science.
Yeah.
First off, the small sample size, just 5 people with complete data, means you can't generalize the findings too broadly yet. You need more people to confirm these initial signals. Second, they didn't have a control group performing the tasks without any music. So it's harder to definitively say how much of the effect is purely the music versus just doing the task itself.
Right. And the music was personal too, wasn't it? Chosen by the participants. Could that play a role?
Definitely. That was another key point they brought up. Because participants use their own music, there's a big factor of familiarity.
The responses might be tied to memories or existing associations with that music, not just its inherent calming or exciting acoustic properties. And finally, a really important limitation. They didn't collect subjective self-reports. They didn't ask people, how focused do you feel or how stressed are you right now? So, a big question for future work is how to blend that subjective, lived experience with all this rich objective data to get an even fuller, more human understanding. But even with those limitations, this data set itself is incredibly valuable. It's like a goldmine for other researchers. It provides a solid foundation, lets people replicate the study, maybe with bigger groups or a control condition, refine the methods, and really accelerate our understanding of how music interacts with our minds. It's a crucial first step.
What an amazing journey we've taken today. Seriously, from just the everyday act of putting on headphones all the way to this incredibly complex, dynamic interplay between our brains and music, measured by the symphony of sensors. The core idea is just profound, isn't it? Music isn't just background noise or entertainment. It's a powerful, non-invasive tool that might actually help us fine-tune our brain states, manage our arousal, and boost our performance. Seeing that journey from subjective feeling to objective measurement is really something else. So maybe next time you instinctively reach for your music, whether you're trying to power through a tough task or just trying to relax, pause for a second and consider this. What if that track you choose isn't just setting a mood, but actively shaping your brain's capacity to learn, remember, and perform at its absolute best? What kind of personal in-back challenge are you trying to conquer with your playlist right now? Keep exploring, keep asking questions, and keep diving deep with us.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Okay, let's unpack this. Have you ever felt your palms get a bit sweaty before, say, a big presentation? Or maybe noticed your breathing change when you're really concentrating on something difficult?
Oh, definitely. Our bodies are constantly talking, aren't they?
Exactly. Sending out these subtle signals. It's like a secret language reflecting what's going on inside. So imagine if you could actually see that language, see it mapped out in real time.
Well, that's pretty much what we're diving into today.
Yeah, we're looking at this really interesting approach called physiological signal, visualization, and simulation. And the whole idea, the data it uses, it's inspired by the multimodal NBAC music dataset. You can find that on PhysiaNet.
Right. And what's fascinating here, I think, is how this visualization really shows the connection, between our thoughts, our cognitive state, and what our body is actually doing physiologically.
So it's making the invisible visible, in a way.
Precisely. Its main purpose is to show really clearly how different signals from the body, like heart rate, sweat, breathing, react when you put the brain under different loads.
Like with a tough memory task.
Exactly, like an NBAC task.
Right.
Or even how they react to different levels of arousal, maybe triggered by different types of music.
Okay.
It's basically a live window into that mind-body link that we usually don't get to see.
So if we're sort of pulling back the curtain on this hidden language, what are the key things this visualization tracks? What are we actually seeing?
Well, first off, you have the NBAC stimulus itself.
Okay.
So you see a sequence of letters popping up on the screen, and this isn't just random. It's a standard cognitive test designed to push your working memory.
Right, like remembering a letter from a few turns back.
Yeah, exactly. Like a 2 back means you check if the current letter matches the one from 2 steps ago. And you can see how that task really demands mental effort.
Okay, so the brain's working hard. What else is changing? What about the heart?
That's where the ECG comes in the electrocardiogram. It measures the heart's electrical activity.
So heart rate, basically.
It shows heart rate, yes. But the deeper insight here isn't just that your heart rate goes up with, say, a harder task or exciting music. It's seeing the timing of that change.
Ah, okay. How quickly it responds.
Exactly. How quickly and by how much it changes right after a specific stimulus. Sometimes you can even see hints of changes in heart rate variability, which tells you about your nervous system's flexibility.
Wow, that's pretty detailed. What about those other reactions, the ones that feel almost subconscious, like, feeling a bit edgy or flushed?
That's where EDA, electrodermal activity, is
Yeah,
interesting.
EDA, right.
Sweat.
Essentially, yeah. It reflects sweat gland activity, which gives you a direct look into your sympathetic nervous system firing up, arousal, stress,
So it's not just stress equals sweat, it's more nuanced.
much more. The visualization lets you see the speed of the response, the size of it, these tiny fluctuations in skin conductance. It gives you this granular detail about your body's arousal level from moment to moment, stuff that's normally totally invisible.
Okay, ECG for the heart, EDA for arousal.
Mm.
What else completes the picture? We also track RESP, which is respiration, your breathing.
Hmm.
You can literally watch how breathing patterns might shift. Maybe they get faster or shallower.
Or more irregular under pressure.
Could be, yeah, under cognitive load or, strong emotions. The visualization just brings these subtle shifts right to the surface, showing how your body is adjusting oxygen intake without you even thinking about it.
And what's really cool, I think, is how you can play around with it.
The interactive part.
Yeah. You can just use a drop-down menu, select different conditions like calm music, easy task, versus exciting music, hard task.
And just watch the simulated signals react instantly.
It's like running your own little experiment on screen. It
Yeah.
makes those connections so obvious, so dynamic.
And if we connect this to the bigger picture, what this really does is hammer home that deep, complex, always-on connection between our mental state, our feelings, and what our body is physically doing.
It's not just a one-way street.
Not at all. It's a constant conversation happening inside us.
So what does this all mean for you listening? Well, it means these signals, your heart rate, your breathing, your skin response, they aren't just random biological noise.
They're telling a story.
Exactly. A detailed, dynamic story about your internal world giving you almost immediate feedback. And just thinking ahead, imagine this wasn't just simulated data. What if it was your real-time data?
From wearables, maybe?
Yeah, data from your watch or sensor. Or what if you could add brain activity visualization, like with FNIRS? And imagine being able to tag events on your own timeline, like just had coffee, deadline looming, finished workout, and seeing instantly how your body responded.
That would be powerful.
What kind of personal insights could that unlock about your well-being, your focus, maybe even spotting health patterns?
Which really raises a huge question, doesn't it? How might actually understanding these subtle dynamic signals, seeing them play out, how might that change how we manage our health, how we learn, or even the small decisions we make every day?
Yes, I said there's a human in the loop. If you have any questions, go for it. Eventually, everything, as the robot said, goes on to BioniChaos.com. So go check it out. Don't forget to provide your feedback. I think we already played the audio for this one. There's a bunch of new tools coming up as well. This one's on Fourier series transform, making art with it. We actually have another one on that. Yeah, we have quite a few things in the works. But yeah, all these tools are currently under development. But if you provide your feedback, we can actually change those or potentially, incorporate your feedback into future web application. We have like this cochlear simulator that you can try out. It shows you how electrodes in the inner ear are being simulated based on the number of electrodes and the incoming sound through your microphone. You can choose your color scheme as well. I like this sunrise one. Okay, let's see if we have time for anything else. Shall we wrap this up? Yeah, if there's any human wants to join in, ask a question, make a comment, suggestion, complaint, we are more than welcome. You are more than welcome. Yeah, looking at VisioNet's list of open access datasets. Yeah, we did cover the interactive brain simulation. We will have an updated version running on the site. This one is already available if you want to try it out, but that will be hopefully we can do it right now. Update. We actually need what do we need? We need a nice sort of thumbnail. We need a thumbnail for it. Need it roughly squarish. Doesn't have to be perfect. Pop it on the... Yeah, the sound there is not great. Pop it on the page. Pop it on the page. Call it... do I have to call it? Yeah, it meant to be a system to... It meant to be a system. The description for the page. Look at the keywords. I might need a better model. Let's try Gemini 2.5. Should be fairly straightforward. Okay, I forgot the keywords. Yeah, I was just trying to publish this one. Yeah, I'm saying everything we do is available on this website. Go check it out. Let us know what you think. Got something playing on the screen while we essentially will be redeploying the site. If you have any questions, there's a human in the loop, or almost a human in the loop. Yeah, that's one that's coming next. Yeah, we need to add a few more things before we can publish it. There are quite a few things. Yep, need this header. Header is good. This Fourier drawing thingy might release as well at the same time. Let's actually see if it's still working or not. Yes, I can do your drawing and it will turn it into Fourier vectors. I can see them over there. Oops, need to slow this down. Can reset view. How do I write? Can do a thumbs up. It will find its center of mass. We have 10 vectors. Yes, the 10 vectors is not enough. Let's increase the speed for a second. So we can add, say, 20 vectors. Yeah, it will follow my drawing a bit more closely. It's pretty good. So like and subscribe. Can slow it down and zoom onto where the current drawing is happening. How do you like that? I find it really cool. But you can reset the view, make it a bit faster. Yeah, there is audio to it as well. There's a sonifications to where the cursor is on the page. Does it look like a thumbs up? I don't know. Probably not. Probably not. Oh, where did it go? Oh, all right. If it's was it deployed? No, it was not deployed. We'll deploy it in a sec. But I kind of like it a lot. Yeah, just need a few components to the page. Yeah, obviously for something more complicated like that, you need to add more vectors. So no, will 25 do? Let's speed it up for a second. Yeah, so it's following. Like, yeah, it looks like a signature. Quite artistic as well, I think. And we can slow it down, zoom onto the thing. Yeah, it's pretty impressive, I would say. But let me know what you think. Yeah, it's based on Fourier transforms. They're used a lot in biomedical data as well. Yeah, I can make nice videos with that. Yeah, and we'll make it available on BioniChaos.com. Well, everything else we do. As everything else we do, it becomes available on our website. We just need to add a header and a description for the page. Apologies in advance, there would be some ads because we need to pay for the server cost. Should try thumbs up again. It's kind of nice if it has a complete drawing. Let's see if it follows it correctly. It's meant to be thumbs up. No, it cannot do it with 10 vectors. Yeah, we need about like 25 or so. Speed it up. Yeah, so going down. Does look like a thumbs up. well, an artistic version of it. So give it a like. Oh, and we need a thumbnail. That's a good one. Goes. That roughly a square. Everyone likes a good dark background. Yeah, and every change we make the page refreshes. Sorry for that. Thumbnail. There's a better one. Like, comment, subscribe, unsubscribe. You know what to do. We're trying to fix the page. Currently using a GPT 4.1. No, let's redo it with 4.0 because some things are just, well, meant to be simpler. Check the page on the server. Yeah, we also have this interactive brain EEG simulation. It's an ICA, PCA analysis. Yeah, we have description, title, keywords. They look good. We have the header, logo. We have a thumbnail. Everyone loves a good thumbnail. It's why how my views drop when I start talking. When the bots are talking, my views go up. How about that? Need to improve the layout and the styling for this page. We normally also have some sort of title. Canvas. When loading the page. Yeah, that may be better. Yeah, 25 vectors is actually, it looks better for most cases. Yeah, very nice. Let's pop it into Notebook LM real quick. It's just the code. Well, the code has a description at the bottom as well, so it should be self-contained. There's some equations at the bottom of the page. Yeah, don't like equations. Well, no one likes equations.
Okay, so picture this. You draw basically any shape you can think of. Could be a
Sure.
circle, yeah. Or something way more complex, like, I don't know, a treble clef.
Or even Homer Simpson, apparently.
Right, even Homer Simpson. And then you just watch as it gets perfectly redrawn, almost like magic, just by these simple spinning circles.
Uh-huh.
So today, that's what we're diving into, Fourier series visualization.
Exactly. And our mission, really, for this deep dive is to kind of get our heads around the core idea behind this, well, this really cool interactive tool.
Okay.
It all goes back to Joseph Fourier, his big discovery that essentially any periodic signal, or in this case, like a closed 2D shape, you can represent it just as a sum of simple sine waves.
Simple ways making complex shapes.
Right. And the visualization, the tool we're looking at, it uses these things called epicycles, rotating vectors. It's actually a term from old astronomy, kind of repurposed here.
Epicycles, like circles on circles.
Pretty much. Yeah. Little rotating vectors demonstrating this whole idea of simple cycles building up something complex.
So that's the core concept then, breaking stuff down into waves. How does this visualization actually, bring that to life? Because it feels really intuitive when you see it.
It really does.
I mean, you can literally draw whatever shape you want or pick from presets. You mentioned Homer, but also like a square, circle, heart.
Treble clef? Yeah.
And you can fiddle with the controls too, right? The number of vectors, how fast they spin.
Yep, exactly. And the how is where it gets really interesting. Each one of those spinning vectors you see, that's one piece, one term of the Fourier series, a building block.
Okay, one vector is one part of the recipe.
Precisely. And the length of that vector, that tells you the amplitude, how big that particular wave component is, the speed it rotates, that's the frequency.
Right. Amplitude and frequency,
And
right.
all the details, the exact size, speed, even the starting angle or phase, it's all packed into these mathematical things called Fourier coefficients, often written as CRAN. That's like the specific instruction for each circle.
So the math tells each circle exactly what to do.
You got it. Then you stick these vectors together, tip to tail, one after the other.
Tip to tail, correct.
The very end point, the tip of the very last vector. That's the point that traces out your original shape.
Wow.
It really is that aha moment, isn't it? Seeing this like intricate shape just emerge from simple circles spinning.
It really is. It feels like finding, I don't know, the hidden clockwork behind something beautiful makes you rethink what simple can do. But, okay, beyond the cool visuals, why should this matter to you listening? What's the bigger picture here?
Well, stepping back, this idea of breaking things down, decomposition, it's incredibly powerful, like really powerful.
Oh, so
It lets us take super complex information, maybe it's an image, maybe it's a sound wave, maybe it's financial data, and just break it into simpler, manageable bits.
right, understandable parts.
Exactly. And think about where that's used. You know how MP3s work. Compressing music, that's Fourier analysis. Or cleaning up noise from an MRI scan in a hospital, same principle. Analyzing vibrations in a bridge for safety. Again, breaking down complex vibrations into simpler frequencies. It's not just theory, it's fundamental.
So it helps find order in what looks like chaos.
That's a great way to put it. And, looking ahead, people could make these visualizations even faster, maybe using something called the fast Fourier transform, the FFT.
FFT sounds important.
Oh, it is. It's basically a super efficient algorithm to do all these calculations, like lightning fast. Essential for real-time stuff with huge amounts of data.
Okay, that makes sense for performance. So if we can break down images and sounds, give me a really concrete, maybe surprising example where this breaking down is crucial.
Okay. How about speech recognition? When you talk to your phone or a smart speaker.
Yeah.
Your voice is a really complex sound wave, right? The system takes that wave, uses Fourier analysis to break it down into all its different frequencies, its basic components.
Ah, I see.
And then it analyzes those simpler frequency patterns to figure out the words you're saying. It has to deconstruct the complexity first.
So it hears the ingredients of my voice, not just the whole sound.
Pretty much. Which kind of leads to a thought, maybe for you listening. If a complicated drawing is just a sum of simple rotations, and a voice is a sum of simple frequencies, what else out there seems impossibly complex?
Like what?
Maybe patterns in the stock market, the weird world of quantum mechanics, maybe even, I don't know, biological rhythms. Could they also be understood by finding their simplest repeating parts? It really makes you question how we even look at complexity.
Yeah, that idea that complexity might just be layers of simplicity. That goes way beyond drawing shapes. It's a whole different lens to view the world through.
It is. And once you start looking for those fundamental pieces, those building blocks, everywhere, well, it can really shift how you see things that seemed messy or random before.
A new perspective unlocked by circles.
You could say that. Understanding the building blocks definitely unlocks a deeper kind of insight.
Yes, per usual, there is a human in the loop. If you have any questions, if I can answer them, we have a bunch of robots that will answer them.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Yeah, just trying to improve a few things before we publish this one. Yeah, trying to add that audio description to the page. Stuffing basic things up. This is a bit better. Okay, so we have the audio thumbnail. The actual web application, all the code is on the page. If you're ever wondering where the code is, the code is on the page. F12 in any browser. Kind of need to do the same. Okay, bear with me. I know it's hard, but you can do it. I have generated an audio for this code, for this application. It's notebook LM. And we will play it here, add it to the page. And I think we'll wrap this up. Yeah, go check the website. Put a big like. I will need to redeploy the website. Do it by the end, at the end of the session. So it's interesting how people complain about AI generated content. But then interestingly enough, when I turn my microphone on, or camera or whatever, the views actually drop. So what does it mean for humans? What does it mean for humans? Yeah, everything we do is on this website. We're deploying this one, drawing with Fourier transforms. We are deploying a new interactive brain AG simulation that focuses on principal and independent component analysis, essentially separating your signal into multiple components. That seemed to work pretty well. Yeah, I'll do this overview real quick and we will sign out.
Welcome back to the deep dive. Today, we're venturing into something really fascinating, incredibly complex, the human brain.
Yeah, it doesn't get much more complex than that.
Exactly. And our mission today is to understand how we can actually, well, listen in on its electrical conversations. How do we make sense of all that activity?
It is quite the challenge.
It is, and we're going to dive deep using this really interesting source, an interactive brain EEG simulation and analysis tool.
Ah, okay. So a simulation to help visualize things.
Precisely. And it tackles this core problem in neuroscience, you've probably heard of it, the cocktail party problem.
Oh yeah, definitely. Trying to focus on one voice in a noisy room.
Right. But apply that to the brain. You've got countless brain regions all sort of talking electrically at the same time. How on earth do you pick out one specific signal when everything's mixed together?
And that's the fundamental issue with EEG, electroencephalography.
Tell us a bit more about that, the basics of EEG.
Sure. So EEG uses electrodes. You place them on the scalp, and they measure the electrical activity firing off in the brain. But here's the catch. Each electrode isn't just listening to the bit of brain right underneath it. No, it picks up a mixture of signals from lots of different areas, some near, some maybe a bit further away. It's like putting a microphone in the middle of that party. You hear the loudest person nearby, sure, but also the general buzz from everywhere else.
That makes sense. It's all blended together.
Exactly. It's a real hurdle for studying brain dynamics accurately.
And this is where this interactive tool comes in, right? It really helps you grapple with that complexity. It's not just theory. You can actually see it, interact with it.
Yeah, hands-on is often the best way to understand these things.
It gives you this kind of shortcut, maybe, to understanding the techniques scientists use to untangle these signals without needing, a PhD first.
Right, it demystifies it a bit.
So let's talk about what you can actually see in the simulation. It starts with brainwaves, doesn't it?
It does. And it visualizes the main types really well. The different rhythms.
5 main ones, delta, theta.
Yep. Delta, that's the really slow one, like 1 to 4 hertz. Dominant when you're in deep, dreamless sleep.
Okay.
Then you've got theta, bit faster, 4 to 8 hertz. That's linked more to drowsiness, maybe light meditation, memory stuff.
Right, I've heard of theta for memory.
Then alpha, 8 to 13 hertz. That's the classic relaxed but awake state, often strongest when your eyes are closed, just chilling out.
The relaxed state.
Pretty much. Then we get faster, beta waves, 13 to 30 hertz. That's your brain when it's busy, active thinking, focusing, solving problems.
So like right now, for us, probably lots of beta.
Hopefully, yeah. And then even faster is gamma, anything from 30 up to maybe 100 hertz. That's linked to higher level processing, integrating information, maybe even aspects of consciousness itself. It's pretty high frequency stuff.
Wow. And the simulation lets you see these different states.
Yeah, that's what the presets are for. Click relaxed and boom, you see this prominent alpha wave activity. Then switch it to active task and you'll see the faster waves, beta and gamma, really take over. It visually shows that shift in mental state.
That's pretty cool. What about the noisy data preset?
That's crucial too. Because real-world EEG is always noisy. You get electrical interference from lights, computers, even just muscle tension. So that preset adds in some of that noise, showing you how easily the actual brain signals can get, well, kind of buried.
Makes it harder to see what's really going on.
Exactly. Oh, and there's a complex mix too, just to show a really busy brain state.
And you can also set things up yourself, the manual mode.
Yes. That's a great feature. You can click on the head diagram, place up to 5 different signal sources wherever you want.
Yeah.
And then you immediately see how the strength of the signal picked up by each electrode changes based on how close it is to your source.
So it really demonstrates that spatial mixing problem. Closer source, stronger signal at that electrode.
Precisely. It hammers home why just looking at one electrode's reading isn't the full picture.
Okay, so we see the problem, the mixed signals. Now, how does the simulation show the solutions? the analysis modes.
Right, the ways we try to fix that cocktail party problem. So the default view is raw signals.
Which is just the messy mix, as recorded.
Yep, just like the microphone picking up everything. Then you can try apply PCA.
Principal component analysis. Sounds technical.
It is, but the concept is about finding the biggest patterns, the main directions of variance in the data. In the simulation, it sort of simplifies this. It visually orders the channels based on their signal power, from highest to lowest.
So it helps you see which signals are most dominant in that mix?
Kind of, yeah. It's a way to reduce the complexity and highlight the strongest components, a first step.
Okay. But then there's ICA.
Ah, yes, independent component analysis.
Right.
This is much more powerful for actually separating the sources.
Like trying to isolate each voice at the party.
That's the goal. ICA algorithms try to mathematically unmix the signals recorded at the electrodes back into their original independent sources. The simulation shows an idealized version of this. You apply ICA, and you can hover over one of the separated waveforms, and you'll see the spot on the brain diagram where that signal likely originated glow.
Oh, wow. So it visually links the separated signal back to its source.
Yeah, it's a really neat demonstration of what source separation tries to achieve, unmixing the mess.
That really clarifies things. Are there other controls in there?
A few useful ones, yeah. You can crank up the noise level to make the challenge harder, simulate different recording conditions.
Makes sense.
You can change the speed, the time scale, so you can see the waves unfold faster or slower.
Okay.
And there's even audio sonification.
What's that?
It turns the electrical signals into sound. So you can literally hear the rhythm of the brainwaves changing. Gives you another way to perceive the data.
Huh. Auditory feedback. Interesting. So, stepping back a bit, exploring this simulation, what's the real takeaway for you listening? It seems like it's more than just learning about a tool. It's getting a real, tangible feel for EEG analysis.
I think so.
Understanding the problems, like the signal mixing, and then seeing, conceptually at least, how techniques like PCA and ICA work to solve them.
Yeah, it provides a clarity that's often hard to get just from reading descriptions. It makes these quite abstract concepts much more concrete.
So it's like a fast track to getting the core ideas without getting bogged down in heavy math right away.
Exactly. It builds that foundational intuition.
Okay, so let's recap the journey. We started with this idea of the brain's electrical activity being like a noisy room, a cocktail party.
All the signals mixed together at the scalp electrodes.
Then we saw how this simulation lets you play with those signals, see different brain states like relaxed or active.
And how analysis methods like PCA start to organize the chaos.
And ICA, conceptually, tries to separate those individual voices or sources.
Right. And understanding these methods isn't just academic. It's really crucial if you want to grasp how researchers actually study brain activity today. It connects directly to all the exciting stuff happening in neurotechnology, brain-computer interfaces, how we're learning to interpret and even interact with brain signals.
So thinking about the future, the source material mentions some potential next steps for simulations like this. Where could this go?
Oh yeah, some really interesting directions. They talked about integrating more advanced algorithms.
Like?
Things like Fastica or Infomax. These are algorithms used in real research for what's called blind source separation, meaning they try to unmix the signals even without knowing where the sources are beforehand. That's a big step closer to real analysis.
Wow. Okay, so truly separating the signals without hints.
Pretty much. And then there's the physical modeling aspect.
Making the head model more realistic.
Exactly. Using actual 3D MRI scans to build the head geometry. And employing techniques like FEM, the finite element method. Yeah, it's a way to simulate much more accurately how the electrical signals actually travel through the different layers, the brain tissue, the skull, the scalp, which all affect the signal before it reaches the electrode.
So adding real physics and anatomy into the simulation.
Right, making it much more biophysically realistic.
What else? Artifacts.
Yes, that would be huge. Adding the ability to simulate common artifacts.
Things that aren't brain signals but get picked up anyway.
Precisely. Like eye blinks, you see those as big EOG signals. Or muscle tension from clenching your jaw, that's EMG. These contaminate real EEG all the time, so letting users practice spotting and maybe even removing them in the simulation would be incredibly valuable training.
Yeah, I can see that, learning to clean up the data.
And the ultimate step, maybe, would be allowing users to upload and analyze real EEG data within the tool.
So bridging that final gap between the simulation and actual research or clinical practice.
That would really complete the picture.
So it really makes you think, doesn't it? This rapid progress in simulating, analyzing, understanding brain signals What does it all mean for our future?
It's a big question.
How could these advancements change things like, say, brain-computer interfaces, or how we understand something as fundamental as consciousness?
Or even personalized medicine, maybe treatments tailored based on an individual's specific brain activity patterns.
And maybe just as importantly, how can tools like the one we discussed keep making this incredibly complex science more understandable, more accessible for you listening, empowering more people to engage with it?
That accessibility piece is key, I think.
Definitely something to ponder. We really encourage you to keep exploring these areas. They're only going to become more relevant.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Welcome to the deep dive. Today, we're jumping into something really fascinating. It's called BioniChaos.
Right. It's this platform that brings together biomedical data, some really cutting-edge tech, and educational tools in a pretty unique way.
Yeah, exactly. And our mission for this deep dive is basically to unpack how BioniChaos takes these super complex medical and biological ideas.
Things that are usually pretty hard to grasp.
Totally. And turns them into experiences that are, understandable, interactive, and honestly, quite engaging.
Think of it as a shortcut, maybe.
Yeah.
A way for you to get informed about some really complex but important areas in health tech.
We're going to look at simulations where you can, peek inside the brain.
And dissect complex signals, navigate these massive medical data sets.
And even touch on some of the ethical questions that pop up.
Yeah, that's important too. Get ready for some aha moments, I think.
Okay, let's start with the brain. Visualizing the signals of thought. BioniChaos has this interactive brain EEG simulation.
Right. And this isn't just, a picture. It lets you actively visualize and explore EEG signal.
It goes deeper too, right, with analysis like PCA and ICA.
Exactly. PTA and ICA, for those who might not know, they're basically smart mathematical ways to find the real patterns and sort of filter out the noise and all that complex brain data.
Makes sense. So it brings brain activity to life for learning.
Precisely. For learning, for demos. And to help with that, there's also the interactive guide to EEG technologies.
Oh, okay. So this gets into the nuts and bolts.
Yeah. Everything from the electrodes, where you put them, how invasive different methods are.
And the different brain waves, delta, theta.
All of them. Delta for deep sleep, theta for relaxation, alpha, beta.
Yeah.
It visualizes how we see these different states of mind. It's key to interpreting those rhythms you see.
Okay, so we can see the signals, but then there's this next tool, the AI-powered EEG speech decoding report. Wow.
Yeah.
I mean, translating brain activity directly into speech, the possibilities just seem huge.
It's a massive leap, really. This report digs into the new approaches trying to make that happen, turning brain signals into actual words.
What's the big insight there, beyond just the tech itself?
Well, I think it's the jump from theory, BCI theory, to potentially practical communication.
Right.
Think about people with severe speech issues or emergency situations, maybe.
Yeah.
It's about giving a voice back, Potentially. That's more than just tech. It's profound. A huge step in how humans and computers might interact.
Absolutely astonishing. And for people wanting to get even more hands-on.
There's the advanced EEG signal simulator. That's where you can customize the brainwaves.
Simulate artifacts, too, those glitches that mess things up.
Yep. Simulate artifacts, see the signals in time and frequency. It's really geared towards researchers, BCI development, that kind of thing.
And building on that foundation.
There are specific tools like Rhythm Scan. This lets you explore real EEG data, visualize things called spectrograms, and understand how machine learning is used for, say, seizure detection.
Which actually leads us nicely into understanding complex signals more generally, not just brainwaves.
Right, because understanding any of these signals, it often comes down to finding the patterns underneath.
So we shift from biology to the math behind it, like Fourier analysis.
Exactly. And BioniChaos has a really captivating tool for this, the Fourier series visualization.
Oh, I think I saw this one. You draw a shape.
Any shape you want, yeah. And then you watch as the tool rebuilds it using a sum of rotating vectors, epicycles, basically.
It's kind of mesmerizing.
It is. And it shows beautifully how even incredibly complex, jagged patterns can be broken down into simple, smooth sine waves.
Which is fundamental to so much, right? Signal processing, sound, images.
Absolutely. It reveals this sort of hidden order in seemingly chaotic data.
I remember when I first tried to learn Fourier analysis, it felt, well, daunting, like math magic. Does BioniChaos help make it less intimidating?
I think so, yeah. That's the whole point of these interactive tools. They have a high-fidelity Fourier simulation, too. It gives you real-time visuals of the signal, the frequency parts, those spinning epicycles. It makes it intuitive, not just abstract equations.
So you can really see the math at work.
Precisely.
Okay, so we have these powerful ways to analyze signals. What about applying this to just the sheer volume of medical data that's out there now? How do we navigate that?
That's a huge challenge, and BioniChaos addresses it with tools like the multimodal medical data landscape, an interactive report.
Multimodal meaning different types of data together.
Exactly. EEG, ECG, imaging, etc. This report looks at publicly available raw data sets, especially for cardiovascular applications.
And it helps you see where the gaps are.
Yeah, visualize the gaps, find ways to maybe connect different data sources, because just having data isn't enough. You need to make it work together.
And there's an Explorer tool for that, too.
The Interactive Explorer. Public, multimodal biomedical data sets. It's a web app specifically designed to help you dig into these varied data sets. EEG, ECG, PPG, FNIRS.
So many acronyms. How do researchers even decide which data type is best for their question?
Good question. That's where the modality comparison bubble chart comes in handy.
A bubble chart.
Yeah, it visually compares different sensing methods based on things like how fast they can measure changes temporal resolution and how precisely they can pinpoint location spatial resolution.
Ah, okay. So it helps you choose the right tool for the job, whether you need speed or detail in space.
Exactly. It highlights those trade-offs, making disparate data work together. It's a big strategic piece.
Okay, let's shift gears a bit. Talk about specific applications, maybe starting with hearing. Cochlear implants.
Sure. BioniChaos has a Cochlear Limited, a visual analysis. This dives into the company, the tech, the history, finances.
But also the ethics.
Yes. Importantly, it includes the ethical discussions and controversies around them. It doesn't shy away from that complexity. It lets you see different sides of the debate about their impact.
Which is crucial for a full picture.
Definitely. And then you can actually simulate how they work. With the Cochlear implant simulation, you can visualize the electrical signals going to the brain, tweak parameters, see how it changes the potential outcome.
Wow. And there's even a 3D simulator for the implant itself.
Yeah, the Cochlear Implant Ring Electrode Simulator. It uses 3D visuals to show the mechanics of inserting the implant. Really shows the precision needed.
Incredible detail. Okay, moving beyond hearing, other vital signals. The heart, for instance.
Right. There's an ECG simulator.
Yeah.
An interactive tool where you can explore different heart rhythms.
Not just normal versus abnormal.
No, you can see how changing different electrophysiological parameters actually affects the ECG waveform you see on the screen. It helps you understand the nuances.
And sometimes these systems are connected, right? Heart and brain.
Absolutely. There's an epilepsy and cardiac health interactive evidence review.
Ah, interesting link.
Yeah, it explores that complex relationship, how epilepsy and heart health interact, the effects of medications, different study methods, clinical guidelines. It's a really important intersection in patient care.
Understanding one helps manage the other.
Often, yes. And speaking of brain imaging, besides EEG, there's FNIRs,
FNRS.
functional near-infrared spectroscopy. It measures brain activity differently by looking at blood oxygen changes, less invasive than some methods.
And BioniChaos has a tool for that?
An FNRS interactive viewer
Yeah.
lets you visualize that time series data, select channels, navigate through events recorded during the scan, useful for certain kinds of neuroscience research.
Okay, fascinating. Lastly, let's touch on two different but key areas. One is the power of the mind itself, like with neurofeedback.
Right, the neurofeedback, placebo or panacea review tackles that head-on.
Placebo or panacea, so it addresses the debate.
Exactly. It looks at the evidence for using neurofeedback for things like ADHD, anxiety, depression. But critically, it compares both the supportive studies and the skeptical views from clinical trials.
So it encourages you to think critically about it.
Precisely. It's not just pushing one view. It highlights the need for really rigorous, balanced assessment of these emerging therapies.
That's really valuable. And the final piece, understanding noise.
Yeah, the stuff that gets in the way of the signal you want to see. The synthetic noise generator dashboard.
What does that do?
It lets you generate and visualize different kinds of noise. White noise, pink, brown, even periodic noise. You can tweak parameters and see how they look in time and frequency.
Why is that useful?
Because you can't really understand the signal or clean it up properly unless you understand the noise that's mixed in with it. It's crucial for interpreting real-world data accurately.
So this whole deep dive into BioniChaos, it really demonstrates how these interactive simulations and data tools can, well, demystify some seriously complex stuff.
Yeah, it makes biomedical information much more accessible and insightful, whether you're a student just starting out or, a seasoned researcher.
The combination of seeing, simulating, analyzing, it gives you a unique window into neuroscience, biomedical engineering, heart health.
It turns data into an experience, really. It's more hands-on.
So wrapping up, what does this all mean for you listening? I think it raises a really interesting question. As these kinds of interactive tools get better and easier to access, could they fundamentally change how we understand our own biology?
How we engage with our own health data.
Exactly. Imagine being able to visualize and interpret aspects of your own health with this kind of clarity. The future of personalized medicine might look very different.
Definitely something to think about, how that interaction might evolve.
Food for thought as we keep exploring the cutting edge.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
Okay, there is a human in the loop. If you have any questions, go for it. Otherwise, we'll call it a day. Yeah, we covered quite a bit of ground today. This Python code, it actually checks the website. Currently we have this 46 like warning messages. Let's see. 46. Yeah, because we added a few things. Now we have 48. Okay, that's not much better, is it? Well, that's mainly because, yes, some of the tools are missing a link on the landing page. So that's not cool. 39 tools are missing a link. It's probably because there's some problem with them or something is missing. So I'll have to look at them again, but yeah, we'll do it next week. We'll do it next week. We will do it next time. Okay, we'll give Notebook LM a rest. Thank you very much, Notebook LM, for providing the professional podcasts. Still have any questions? Pop them in the chat. Just one last thing. Before we forget, okay, we have this tool in Gemini. This actually looks pretty decent. The link to a data set. That's what I'm talking about. It's actually showing you a real-time simulated visualization of multimodal physiological data. Yes, so we're recording ECG, EDA. It's your essentially sweat on your hands and respiratory signals, and that's what's happening in this data set here. So we might be actually looking at real data later on. But it's just a simulation of what's going on, and it's a memory task where you have to remember 1 back or 3 back, a sequence of letters. So you can have a demo here, which is already playing, so I'm not sure why the play button. You can have audio for the heartbeats. It's actually quite a nice audio. Now it's going faster. Very nice. So I like this simulation demo of essentially behavioral study, memory testing. Working memory in presence of music. So it's meant to be music playing as well. Yeah, might keep chipping away on this one, try and make it better, but it's pretty decent as it is. So it might be, again, everything we do is available on BioniChaos.com. Go check it out. Let us know what you think, and don't forget to like, subscribe, unsubscribe, whatever you need to do. And if there's no questions in the chat, I'm streaming normally on YouTube pretty much daily. Let's check LinkedIn as well. We're streaming on LinkedIn as well. Yeah, I'm not sure what's happening with that stream, but yeah, I'll see you next time. Bye.